We are back to another wonderful section of our calculus, and this session we are taking a related rate, that is after the implicit differentiation. Related rate is an interesting topic because it helps us to apply the implicit differentiation we've done. Now, what is the concept of related rate? Related rate is a way we are able to find the rate at which something changes. The rate at which this is changing given another variable change. And let me change the pen as usual. The rate at which this guy is changing given that this is already changing, and that is a concept of rate of change. No, that is a concept of related rates. Sorry. Again, because we are going to use the implicit differentiation, means that our chain rule becomes or will come handy. Let's not forget about that. Let's take a quick example. With example 1, we are given a variable or relation y is equal to 2 minus 4x, and then we are given that x and y are functions of t such that certain things are given, and we are asked to find something else. And the question, our focus is to find dy dt. So I have the question mark here. Dy dt, is the same as y prime of t. But what were we given? We are given the x dt equal to 10. Just that is given. So we are given the rate of change for x, and we expect to find the rate of change for y. And that is a concept again of related rate. Now, because I have x depending on t and y also depending on t, it's as if I have this function here. So I will write the relation as y of t is equal to 2 minus 4 over x on t. So I'm able to apply the implicit differentiation. So the independent variable is d dt of yt is equal to d dt of 2 minus d dt of, I want to have it at 4x of t minus 1. I'm just taking it up. This is the same as dy dt is equal to 0 minus, I apply the implicit differentiation here. It's means I'm going to have the 4x over the x times the x dt. And this is going to give me there's negative 1 here. So negative into bracket negative 4x squared times the x dt. The x dt is given in the question. Sorry. And I'm going to get 4x negative 2 times 10. This is the same as having 4 over x squared times 10, which is equal to 40 over x squared. And so that is the rate of change of y respect to t. Let me check the answer. Yeah, so that is our right answer. Example 2. We are going to now take a word problem. With this second example, we are taking a word problem. I'm always interested in word problems because it helps me apply my understanding. If I'm not able to do that, it means I don't understand the concept. We are looking at a falling ladder. This is a very simple scenario for all of us. It says that a 5 meters ladder is leaned against a wall at 3 meters away. So I have a wall here, and assume this is the floor. The ladder, the bottom of the ladder is 3 meters away, but the ladder itself is 5 meters. I want to have that as z. It says, imagine you climb to the top of this ladder and then it starts to slip. So there's the first stage, stage 1, and then stage 2, it slips a bit. So look at where it slipped to. Stage 3, you slip to this point. You'll get to a final stage where the ladder will just fall flat on the floor. And these are the rates of changes as the ladder slips over. The question is, how fast is the bottom end of the ladder sliding from the ground? And here we are asked to take x to be the distance from the wall to the bottom of the ladder. The distance from the wall to the bottom of the ladder as x, and then the distance from the ground to the top of the ladder as y. If I want to write this out very well, or draw this diagram. It's as if I have it as simple this way, where I have my hypotenuse as 5, my opposite as y, and adjacent at 3. If you went through the algebra lecture series with me, you can see that we can find y by simply having 5 square equal to y square plus 3 square, and so y square will be equal to square root of 25 minus 9, that is 16. That is plus or minus 16, so y will be equal to positive 4. Y can't be negative 4 because y is a length of a wall. Okay, so you can't have negative centimeters. We've found y. But what is the focus here? The focus is to find the change in x with respect to t. Why not change in y? Why change in x? Change in x because we are looking at how fast the bottom of the end of the ladder is sliding from the ground, and that is the x part. What are we given? We are given the small change in y to be negative 1. In the question it is 1, but because it is a downward movement, the velocity has to change to negative 1. We are giving z as 5, that is the length of the ladder. We are giving x as 3, that's the distance from the wall to the ground. Now the relation I can rewrite it as from the Pythagorean theorem. Z squared, the hypotenuse square, is the sum of the adjacent and then the opposite. If I want to write it in an implicit expression, this is already in an implicit form. I have to now take everything in terms of x for y and then x. And now to differentiate respect to t of that, respect to t of that, respect to y square of that. So everything drops. Now this goes to 0. Over here I have to apply the implicit differentiation. I'll go straight to write the answer 2x x prime. And here to have to apply the implicit differentiation, I'm going to get 2y y prime. I know you can go through that and get it. And so this go to 2 into brackets. No, because I want x prime, I could have x prime out. 2x plus 2y equal to 0. Is that correct? I've done something wrong. No, this is not correct. So I can have it as negative 2x x prime is equal to 2y y prime, where x prime will be equal to 2y y prime all over negative 2x. This is the same as having y y prime over x, and that is how fast the ladder is sliding from the ground. But we are giving certain parameters. Now x prime negative y we had 4, y prime was negative 1 all over x was 3, and so by substitution I have 4 on 3, which is equal to 1.333 meters per second. So the x dt is per second because of the time variable. So the sliding at a rate of 1.33 meters per second, which makes sense because if I move up here, as this is reduced, this wall is reducing by 1 meters per second. I expect that as it's dropped, it would be elongated at the ground, and so it should be more than the 1 meters, which is what we are getting, 1.33. That makes sense. Okay.
Dr. Baldry.
Now to example 2. That is what I have my slide 13. You can just pause the video and go through slide 13 if you didn't get the analogy. Now we are not moving to example 2 yet. We have to repeat our calculations for the rate at which the bottom end of the ladder is slide when the top of the ladder just hits the ground. And that is my last stage here. We are looking at this, a stage where the ladder just falls to the ground. What is the rate of change? This, I don't need to even work things out. I can simply tell that the rate of change will be 0 because it does not change. The ladder does not change. There is no movement. But if you want to verify that mathematically, it's like what I have here. This is 3, this is y. Now z is here. It is not this way to have it as a right angle triangle. Z has fallen flat, just as I have here. And so the x, the y, we had y prime over x. It means at this point y is 0, y prime was -1, and then x was given as 3, and that is 0. It means there's no change, or the ladder does not even move at all, it is flat on the floor, and that is the answer. Now example 3, that is the last example, then we take our problem of the day. Example 3, we are looking at production cost. In the production cost, it says the total daily cost in dollars of producing some items X is given by whatever function we have there. If the production has been ramping up by 20 items a day, find the rate at which total daily cost is increasing, and if they are currently producing at 200 items per day. The focus is to find a small change in the total cost of production. You must always know your focus before you even start working. And then ask yourself, what are the terms given? I'm giving the total cost function. Is that all? No. I'm giving the quantity of items produced per day, or initial items produced. What else am I giving? I'm giving the small change in production. It says it is ramping up. It means that every day there's increments of production by 20, and that is given by the XDT, because the quantity is in X, and as time progresses it increases by 20. So after all, now rewrite my function in terms of X. Wherever I see X, I introduce the T to have the implicit differentiation done. So I have ddt of TC, ddt of the 300,000 here, ddt of the 4xt, ddt of the 200 million x -1. You want to just take your time and write these things right for me. Okay, now they're the same as the TC dt. Here I have to apply the, okay, so this part goes to 0 plus. Now I have to apply the implicit differentiation here. So ddx of 4x dx dt. I have to apply the implicit differentiation here. ddx of the 200 billion negative x1 dx dt. And so this gives me 4 times dx dt plus or minus 200,000 x squared, x minus 2. Let me just bring it as over x squared. And then we have dx dt. I hope this is not cumbersome to follow. I just hope so. And so this is the same as 4x prime minus, let me just go through my solutions here with you. Yes, I'm correct. Minus 200,000 over x squared x prime. And that is it. But you know, you have been given x prime, you've been given x. So 4 times x prime was 20 minus 200,000 all over 20 square times 20. I think I've done some mistake here. X is not 20, x is 2,000 square. It's x prime, which is 20, and that gives me 79. So that is the cost per day, the rate of change at which your cost is increasing. Your cost of production is going to increase at $79 per day, given that you are producing, or you are changing the production 20 items per day. I hope these two examples have not been confusing and has been well explained. And on to the interesting part of the journey is to have the second problem of the day. In this, we are taking the ideal gas law. The ideal gas looks at the pressure relation of molecules in a system, or in a tube, or in a pipe, or in a container, how these molecules react to each other. It is saying that given constant pressure and then volume, it is directly proportional to the gas rate, or the gas constant, and the temperature, as you can see in the diagram in slide 17. If I take away the directional probability, I can have equal to, and then I introduce a constant of proportionality n. So you ask us, so what is the focus? If you read the problem very well, the focus is to find the rate of change in pressure with respect to time. And what are the variables given? N was given, T is given, R is also given. These are obvious things, but what is not obvious is the V. The V is given as it has moved from 3 liters to 1 liter, so that is 2. We're also given the small change in V, so it is 1. Taking the difference is always the final minus the initial, so over the time. So 1 minus 3 over 60, and that will end up giving me negative 1 over 30 per seconds. And so these are given, and so you go back and write your relation. Now because you are looking for the PDT, it means that you must introduce your independent variable t, and the VDT is also given, so we introduce them here. Alright, and then you take your derivative at both sides. You want to take your time and go through this and then see the answer you're going to get. At the end of the day, I expect the answer to be, I expect the PDT to be equal to 113.49 Pascal. Alright, so you want to verify this answer for me. Thank you very much. And then we also have to find, unless I forget, we have to find the rate halfway in the system. Halfway in the system, I expect the answer to be 113.49. This is the right answer. But before that, I'm supposed to get, so let's do a correction here. In the actual PDT, I'm supposed to get 189.526 Pascal. Alright. But to have the halfway in the container, then I'm going to get 113.49 Pascal. So you want to verify these answers for me. Thank you very much. And then our last episode on our differentiation is extremes of function. Stay tuned, and then let's have fun as we study. Bye.